interval of convergence, one of three things can happen. So when we're trying to find this, one of three things could happen. It may only converge at x equals 0 or the center. Again, we're going to do these for Taylor as well as for our Maclaurin polynomials. So if it's a Maclaurin polynomial, it's only going to converge at x equals 0. I call this your worst case scenario. The idea is to develop a Maclaurin or Taylor polynomial that would have an interval of convergence of all real numbers. That is your best case scenario. If you're only having that one point converge, that's going to be your worst case scenario. It converges absolutely and hence converges for all real numbers. So again, that would have an interval convergence of all real numbers. This is going to be your best case scenario. The best case scenario is when it converges together for your all real numbers. The middle of the road is where you do have an interval of convergence, but it's over some finite open interval. We'll call this from negative r to r, and diverges other places. Again, the series may converge absolutely, or converge conditionally, or diverge at these particular endpoints. This is where all those tests are going to come back in. So at the endpoints of this finite interval, the interval of convergence, it may converge, it may diverge at the endpoint. So you want to check and see what's happening at those particular endpoints. Like I said, this is your middle of the road. You may think it's your worst case scenario because this is going to require more work for you to do. It's going to bring back all those convergence tests that we studied back from 9.1 to 9.6. But in terms of graphically what we're looking at, it is the middle of the road scenario. It's not our best, it's not our worst case. So like I said, it may converge just at the center, x equals 0, or it could be infinite. For this region, the convergence set of a power series of x is called the interval of convergence. In the case where the convergence is a single value, which again, this is just the center, we say that the series has a radius of convergence of 0. When we talk about the radius of convergence, it's how far out from the center is the convergence going. So it's basically, think of the center just like that, the center, and the radius, again, we'll look to the left and look to the right of the center to see exactly how far spread out this particular interval of convergence are. In the case where the convergence set is all real numbers, then we say that the radius of convergence is infinite. And in the case where the convergence extends between negative r and r, we say that the radius of convergence is r. Again, this will actually be a number that we calculate. We'll find the value of this particular radius of convergence. So when we take a look, for example, of these three possibilities, your worst case scenario, here's your center. When you only have convergence at the center, we say the radius of convergence is 0. It's not spreading any further out than that particular center. So again, this is what we call your worst case scenario. If it converges infinitely, then we say the radius of convergence is infinity. And again, this is your best case scenario. Seems like a little blurry to me. Again, your middle of the road, if you have a finite interval, then we say the radius of convergence is r. So again, here's your center at 0. So when we talk about the radius of the convergence, like I mentioned, it's the distance out from the center that the convergence is going to go. So again, it would be, once we calculate this value, it would be, let's say, for example, 5 units to the right of the center, or it's also going to be 5 units less than the center. So that's the radius of convergence. And like I said, this is your middle of the road. As I mentioned, when you do have the middle of the road scenario, 4 things can happen. First of all, the endpoints may be included in the interval of convergence. So we would include the endpoints in the interval of convergence. It's possible that neither of the endpoints are going to be included in the interval of convergence. They're going to diverge at those particular endpoints. It's possible that one will converge, the other one will diverge. So again, like I mentioned, we're going to have to check to see what's happening at each endpoint to see if we're going to include them in the interval of convergence. So how are we going to exactly calculate the interval of convergence? We're going to use to apply the ratio test for absolute convergence. So to find your interval of convergence, we're going to go back and look at your ratio test for absolute convergence. If you remember your ratio test, the limit as k goes to infinity of the absolute value of u sub k plus 1 divided by u sub k. So if you remember by your ratio test, if it was greater than 1, we had divergence. If it was less than 1, it converged. If it was equal to 1, it was inconclusive. How is this going to help us in terms of figuring out what scenario we have, your worst, middle of the road, or best case scenario? So when you perform your ratio test, if you have the value of the limit to be less than 1, then what happens, we know that this is going to converge absolutely. So what happens is you're going to have a radius of convergence of infinity. We have absolute convergence. So going back to your diagram, how do you know when we have this radius of convergence is infinity? After you do your ratio test, if it's less than 1, then you know you have your best case scenario. If you do your ratio test and it's greater than 1 or infinity as your limit, then we know we have divergence. So what's happening is we'll actually have a radius of convergence of 0. We have your worst case scenario. So when you do your ratio test, if it's greater than 1 or infinity, that's how you know you'll have your worst case scenario where you'll have a radius of convergence of just 0. If it's equal to 1, that's where you're going to have a radius of convergence equal to r. That's going to be your middle of the road. So this is when you have your ratio test equal to 1. So, like I said, you're going to think the two best cases is when you find that when you do your ratio test, you find your limit to be greater than 1 or less than 1. It's going to get, because you basically can stop. But the problem is, if you have that middle of the road scenario, you've got to check the endpoints to see if you're going to include them in the interval of convergence. So let's take a look at this particular series. We want to find the interval and radius of convergence. So we're going to perform the ratio test. So the first thing we're going to do is we're going to find the radius of convergence. And we find the radius of convergence by using the ratio test for absolute convergence. So we know by the ratio test I'm going to find the limit as k goes to infinity. Remember, it's the absolute value. U sub k plus 1 is my x to the k plus 1. So that's x to the k times x to the first. All over u sub k, which is my x to the k. You want to simplify this, obviously, so we can cancel out that x to the k. So I have the limit as k goes to infinity of the absolute value of x. So now, using your properties of limits, I'm concerning myself about finding the behavior as k goes to infinity. So what you're going to do after you perform the ratio test is you're going to factor out, or you're going to pull out that absolute value of x, because the absolute value of x is not affecting this particular limit. So I have the absolute value of x times the limit as k goes to infinity. Well, when I factor out the absolute value of x, that's just going to give me a 1. And what is the limit of any constant? The limit of any constant is just going to be that particular constant. So the limit's just going to be 1. So what scenario do I have? Do I have the middle of the road, best, or worst case scenario? Middle of the road. So then, to find my radius of convergence, I'm going to force, remember, to converge. The absolute value of x is going to be less than 1. To converge, the absolute value of x has to be less than 1. So whatever you factor out or whatever you pull out, what you're going to do if you have this middle of the road scenario, we are going to take the absolute value of x and set it less than 1. So now, once you've got this absolute value already isolated, so again, you may have to multiply or divide if you have constants. We'll do an example where there's some constants. Again, once you get the absolute value all by itself, your radius of convergence is that constant right there. So what that tells you is that my radius of convergence is equal to 1. It may not always be 1. I may have an absolute value of x divided by 3. In that particular case, I'd have to multiply by 3, and I'd have a radius of convergence of 3. Now, looking here, thinking about your Maclaurin or Taylor, what's the center of this? Is this a Maclaurin or is this a Taylor? What's the center of this particular series? It's a Maclaurin. So my center is at x equals 0. So there's my center. So I know my radius of convergence is 1, so one of my endpoints is going to be at 1. The other one is going to be at -1. Again, that's your radius of convergence. So any questions so far? So now what you have to do is you have to check your endpoints. So you have to check your endpoints to see what's happening, whether they're going to converge or they're going to diverge at the endpoints. So let's go ahead and let's check x equals 1. So what you're simply going to do is you're going to take 1, plug it back into your original series for x, and go back to all your convergence and divergence tests. So to check at x equals 1, again, I have k is equal to 0 to infinity of 1 to the k. What's going to be a good test to use on this? Divergence test. So let's, by the divergence test, remember, I'm going to take the limit as k goes to infinity of 1 to the k, which is just going to be equal to what? 1 or infinity. Exactly. So is this thing, we know it's not equal to 0, so this thing's going to diverge. So I'm not going to include 1 in my interval of convergence. So now we need to check x equals -1. So again, I'm going to take -1 and plug it into this series. So I have -1 to the k. So what test is going to be a pretty obvious test we're going to use? We're going to start with the what? Is this an alternating series? Is it an alternating series? Yes. So again, we can check the alternating series test. We can find the limit as k goes to infinity. Remember, you slip the alternator, that's going to be a 1 to the k. It's not going to pass your alternating series test because it's going to be equal to infinity or 1, so it is going to diverge by your divergence test. So we're not going to include -1 either. Okay? So then my interval of convergence is going to go from -1 to 1. My radius of convergence is equal to 1. Okay. So any questions on how you can find the, like I said, you're going to think the middle of the road is actually the worst case scenario because you're going to have some more work to do because you've got to check those endpoints. All right, let's take a look at another example. And if this was a Taylor series, we would do it exactly the same way. You'd still have to perform your ratio test. You'd find the limit. So let's take a look at x to the k divided by k factorial. Again, you start by your ratio test for absolute convergence, so the limit as k goes to infinity of the absolute value. X to the k times x to the first divided by k plus 1 factorial, divided by u sub k, so I'm going to multiply by the reciprocal. Again, I know I can simplify k plus 1 factorial down to k plus 1 times k factorial. So the k factorials will cross cancel, the x to the k's will cross cancel. So I'm left with a limit as k goes to infinity of the absolute value of x all over k plus 1. Again, I'm concerning myself with the limit as k goes to infinity. So what can I factor out of this particular? I can factor out the absolute value of x. So the absolute value of x times the limit as k goes to infinity of the absolute value of 1 over k plus 1. What's that limit going to be equal to? That limit's going to be equal to 0. Exactly. So this limit's equal to 0. And 0 is less than 1. So what scenario do I have? Your best case, worst case, or middle of the road? Best case. So again, this is going to give me a radius of convergence equal to infinity. And my interval of convergence will be from negative infinity to infinity. Okay? So since your limit was less than 1, you had that best case scenario. So any questions, and you're done. And you're done. All right? So this is your best case scenario. Any questions on that one? Let's take a look at C. K factorial times x to the k. Again, we're going to use the ratio test for absolute convergence. So I'm going to find the limit as k goes to infinity. Absolute value, again, it's going to be k plus 1 factorial times x to the k, x to the first, all over k factorial times x to the k. Again, those x to the k's will cancel. I can rewrite k plus 1 factorial as k plus 1 times k factorial, so the k factorials will cancel. So then the limit as k goes to infinity, I'm left with the absolute value of k plus 1 times x. So what can I factor out of this particular limit? I can pull out the what? Absolute value of x. So I have the absolute value of x times the limit as k goes to infinity of k plus 1. What's the limit? Infinity. So again, infinity is, I know, greater than 1. So what case do I have here? The best, worst, or middle of the road? Worst case scenario. So again, my radius of convergence is 0. The interval of convergence is not 0. It's just wherever the center is. So this case, your interval of convergence is just the center. So that's at x equals 0. Again, if this was a Taylor, it's not going to be at x equals 0. It'd be somewhere else. So any questions on how you know which scenario you know that you have? Okay. Now let's take a look at D. Now D, I do know I have the alternator, but I'm doing the ratio test for absolute convergence, so I'm taking the absolute value when I do the limit. So I can just simply drop that alternator since I'm doing the absolute value. So I have the limit as k goes to infinity, the absolute value of x to the k times x to the first over 3 to the k times 3 to the first. Now be careful, this is k plus 1, which will give me a k plus 2. Divided by or multiplied by the reciprocal, 3 to the k, x to the k, all over k plus 1. Oh my God, wait a minute. 3 to the k, wait a minute, I mixed this up, k plus 1 over x to the k. I started with the reciprocal and then went back to the original. So I can cross cancel this 3 to the k, cross cancel the x to the k. So I have the limit as k goes to infinity, the absolute value of x times k plus 1 all over 3. And the k plus 2 on the bottom. Now, the one thing, ladies and gentlemen, you have to do, not only when you're doing the absolute convergence, you not only are going to factor out the absolute value of x, but you also want to pull out any constants. If you do not pull out the constants, you're going to interpret the ratio test incorrectly. So when you pull out the absolute value of x, you're also going to pull out the absolute value of x over 3. And look at the limit as k goes to infinity of the absolute value of k plus 1 over k plus 2. So what's the limit as k goes to infinity of the absolute value of k plus 1 divided by k plus 2? 1. Had you not pulled out that 3, what would you have said this limit was? 1/3, and you would have said 1/3 less than 1, and you would have thought you had the best case scenario. So not only do you have to pull out the absolute value, you've got to pull out the constants as well. All right? So what case do I have? Best, worst, or middle of the road? Middle of the road. So again, to find that radius of convergence, I have to take whatever I factored out, the absolute value of x over 3, and find when it's less than 1. You want to solve for the absolute value of x, so what are you going to multiply by? You're going to multiply by 3. So the absolute value of x then is less than 3. So now I have a radius of convergence that's equal to 3. That's your radius of convergence right there. So then my interval of convergence. This is a Maclaurin polynomial, so I know my center is at x equals 0. Think about when you generate a Taylor. You'll know whether it's a Maclaurin or a Taylor because we know if it's a Taylor and the center is not at 0, you're going to see parentheses of x plus or minus the center. If you think about how you generate your Taylor polynomials. So there's nothing added to x, you know it's got to have a center of 0. So then I know that here's my center. So my radius of convergence is going to be 3 more than the center, so I know it's going to have one endpoint at 3. And then it's going to be 3 units less than my center, which is going to be at -3. And then I would have to check the endpoints, which we'll do when we come back from lunch. Okay? So I'll see you guys after lunch. Plug 3 and -3 back into your original function, your series, in order to figure out what's happening going back to all our convergence or divergence tests. So let's check x equals 3. So when I check x equals 3, what I'm going to do is I'm simply going to take 3 and plug it back into my series for x. So I have k is equal to 0 to infinity of -1 to the k, 3 to the k, all over 3 to the k times k plus 1. And again, I can simplify because I can cross out the 3 to the k's. So I'm left with -1 to the k in the numerator, all over a k plus 1. So what test, going back to your belt, your tool belt, what series test do you think we could try and use on this? Well, first of all, it's pretty obvious because what kind of series do we have here? We have an alternating series. So let's try the alternating series test. Remember the alternating series test, we're going to strip the alternator. We want to find the limit as k goes to infinity of 1 over k plus 1. And what's happening with that particular limit? It's equal to what? 0. So it passes the first part of the alternating series test. What's the second condition you have to check? Decreasing. So we have to check that 1 over k plus 1 is greater than 1 over k plus 1 plus 1, or 1 over k plus 2, which it is. So therefore we know that it is going to converge at x equals 3. So we are going to include 3 in my interval of convergence. So now we have to check what's happening at x equals -3. So I'll plug -3 back into my power series for x. So I have k is equal to 0 to infinity, -1 to the k, -3 to the k, all over 3 to the k times k plus 1. And again, you want to simplify this fraction as much as you can before you decide what series test you're going to use. What is this fraction going to simplify down to? Well, what's going to happen with this alternator in the numerator? It's going to cancel out, because no matter what power k is, if it's a negative times a negative, it's going to become a positive. All right, so this is just going to be a 1 in the numerator all over k plus 1, because this is just going to become 3 to the k. So we have 1 over k plus 1. So what test would be a good one to use on this? You could do polynomial. You could do your polynomial test, right? One of your favorites. So again, we've got 0 plus 1 is greater than or equal to what? By your poly test. So what's happening at x equals -3? Is it going to converge or is it going to diverge? Diverge. So I'm not going to include -3 in my interval of convergence. So my radius of convergence is 3. My interval of convergence is going to go from -3 to 3 with a bracket. So any questions on that particular example? Okay. So like I said, if you have a Taylor series, to finding the interval and radius of convergence in a Taylor series, the process is pretty much exactly the same, except the center is no longer at x equals 0. Remember, how do you know you have a Taylor versus a Maclaurin? Remember, you're going to see a number added or subtracted to x inside the parentheses. So this is a Taylor series when you see that number added or subtracted to x. So one of 3 things could happen, just like when you're trying to find the interval and radius of convergence for a Maclaurin series. The series may converge only at the center. And again, like for the Maclaurin, this is your worst case scenario. It may converge absolutely, and it will converge for all real numbers of x. Again, this is your best case scenario. It may converge in some finite open interval. So it may be over your interval x sub 0 minus r, x sub 0 plus r. May be that interval of convergence. And again, at the endpoints, it may converge absolutely, conditionally, or diverge. Again, this is your middle of the road, just like it was for the Maclaurin series. Again, just like we did for the Maclaurin series, if it converges for these powers of x, we call this the interval of convergence. Again, if it converges just at the center, we would say that the radius of convergence is 0. If the whole interval of convergence is the entire real number line, we say the radius of convergence is infinity. If it has a finite interval, we say that the radius of convergence is r. So really the only difference is when you're looking at the 3 cases scenario, the center is no longer 0. So like I said, if you're converging just at the center, we say the radius of convergence is 0. Remember, this happens when the ratio test is greater than 1 or infinity. Again, this is your worst case scenario. If it converges for infinity, we say the radius of convergence is infinity. And again, this is going to happen when your ratio test is less than 1. And again, this is your best case scenario. If you have the finite interval, we say the radius of convergence is equal to r. And again, this is your middle of the road. And this happens when your ratio test is equal to 1. So when you take a look, excuse me, at this example, you have x minus 5 raised to the k over k squared. Notice inside your parentheses you have a number added or subtracted to x. So right away, this is not a Maclaurin, but this is a Taylor. What's the center for this particular Taylor series? 5. So you're still going to perform, to find your radius of convergence, you're still going to perform your ratio test for absolute convergence. So I'm going to find the limit as k goes to infinity of the absolute value. U sub k plus 1, so it's going to be parentheses x minus 5 raised to the k plus 1, or x minus 5 to the k, times x minus 5 to the first, all over k plus 1 squared. Divide by my reciprocal, divide by u sub k, or multiply by the reciprocal, which is k squared over x minus 5 to the k. Simplify as much as you can, so my x minus 5 to the k will cancel. What can I factor out when I'm trying to find the limit as k goes to infinity? I can factor out the what? Absolute value of x minus 5 times the limit as k goes to infinity. So I'm left with k squared over k plus 1 to the second. So what's that limit going to be equal to? That limit's going to be equal to 1. So which scenario do I have? The best, worst, or middle of the road? Middle of the road. So to find the radius of convergence, I have to find where the absolute value of x minus 5 is less than 1. So the absolute value that you want to make sure is solved for, things you want to check for, you want to make sure the coefficient of x is equal to 1. You can't get rid of that minus 5. Remember what that minus 5 is telling you. That minus 5 is telling you the center for this particular tailor. So what's my radius of convergence going to be? My radius of convergence is going to be equal to 1. So what that tells me, now remember, your center is no longer at 0, your center is at 5. So since my radius of convergence is 1, I know I'm going to be one more unit than my center, which is at 6. So there's my radius of convergence, and 1 unit less than my center, which is going to put me at 4. So now the question is, what's happening at those endpoints 4 and 6? So let me go ahead and let's check x equals 6 first. So I'm going to plug 6 back into this particular series for x. So I have k is equal to 1 to infinity. Well, 6 minus 5 is just going to give me 1, and 1 to the k is just 1 over k squared. So what's a good test to check for convergence or divergence? One of your p-series. So by your p-series, what's happening with 1 over k squared? It's going to be what? Converging. So I know 6 is going to be included in my interval of convergence. So next I have to check 4. So I'll plug 4 back into this particular series for x. So k is equal to 1 to infinity. Now 4 minus 5 is going to give me a negative 1 to the k over k squared. What test am I going to use on this one? AST, your alternating series test. So I need to find the limit as k goes to infinity, strip the alternator of 1 over k squared. And that's going to be equal to 0. And again, to check that it's decreasing, 1 over k squared has to be greater than 1 over the quantity k plus 1 squared, which it clearly is. So what's happening at x equals 4? Is it going to be included or not included? Included, so it's going to converge. So then my radius of convergence is 1. My interval of convergence is equal to 4, 6. So like I said, the process is the same that we just did for the Maclaurin. It's just recognizing that it's a Taylor over Maclaurin. The center is not just at 0. All right. The one you have to be careful of is when the center may not be a nice, pretty integer. So take a look at B. What do you think? We can clearly see that this is going to be a Taylor. So the question is, the center may not always be a nice, pretty integer. What's the center going to be here? The center is going to be at x equals what? Negative 2/3. So when you go through the process, again, you want to still do your ratio test. So I'm going to find the limit as k goes to infinity of the absolute value, u sub k plus 1. So I have 3x plus 2 to the k, 3x plus 2 to the first, all over, now be careful, let's talk about this 2 raised to the 2 times k plus 1. When I add 1 to k, look what happens in that numerator. It's going to be 2 raised to the 2k plus 2. Does everybody agree with that? So then remember, I can rewrite this as 2 raised to the 2k times 2 squared, which is 4. Divide by u sub k, or multiply by my reciprocals. That's going to give me 2 raised to the 2k all over 3x plus 2 raised to the k. So I can cross cancel this 3x plus 2 to the k. I can cross cancel this 2 raised to the 2k. Remember, I'm only concerning myself with the limit as k approaches infinity. You want to factor out the absolute value of the expression that comes with an x, as well as your constants. Notice here's my expression, the 3x plus 2. I also have a constant in the denominator. What constant can I pull out? I can pull out that what? 4. So I have the absolute value of 3x plus 2 over 4 times the limit as k goes to infinity, and the only thing I'm left with is a 1. So what's the limit as k approaches infinity of 1? That's just going to be what? 1. So what case do I have here? Best, worst, or middle of the road? Middle. You may think it's the worst case scenario, but it's the middle of the road. So again, what we have to do now is we have to find the radius of convergence, because it's not infinity and it's not 0. So to find where it converges, I have to take 3x plus 2 over 4 and make it less than 1. Well, first of all, what constant can I multiply both sides by? I can multiply everything by what? 4. Now, in order to identify the radius of convergence, the coefficient of x, kind of like when we have to do those horizontal shifts, you've got to make sure that the coefficient of x is a positive 1. Remember, you told me in the very beginning that the center is negative 2/3. So we have to rewrite this just like we would a horizontal transformation. So what I'm going to do is factor out the 3. So I have the absolute value of 3 times x plus 2/3 less than 4. Because you need to have what's inside the absolute value. You need to have that coefficient of x be a positive 1. Now what can I divide both sides by? I can divide both sides by a 3. So I have x plus 2/3 is less than 4/3. It's got to be in this format before you can identify what the radius of convergence is. The coefficient of x needs to be a positive 1. And it's only plus or minus the value of the center. So when the center is not a nice pretty integer, you're going to have some algebraic manipulation to do to get that coefficient of x to be a 1. So now what's the radius of convergence going to be? The radius of convergence is going to be 4/3. So now remember, your center is at negative 2/3. So now that you know your radius of convergence is 4/3, you have to add 4/3 to negative 2/3. So negative 2/3 plus 4/3 is going to give me an endpoint of 2/3. Then you have to subtract 4/3 from negative 2/3. So my other endpoint is going to be at what? Negative 2. Okay? So you guys go ahead and see if you can tell me what's happening at those endpoints, if they're going to be endpoints. Again, like I said, you want to simplify as much as you can those particular expressions. You end up, remember, 2 squared to the k can be written as 2 squared raised to the k power. So really what that denominator is, because when you have a 2 squared, 2 to the 2k, that's actually equivalent to 2 squared raised to the k power. So you really have a 4 to the k down there in the denominator. So any questions on why it's diverging at both of those endpoints? So then my radius of convergence, we found to be 4/3. the interval of convergence is equal to -2 to 2/3, and again with parentheses around both of those. So the center may not be a pretty integer. So when that center is not a pretty integer, before you identify that radius of convergence, you've got to manipulate, just like you would a horizontal shift when you have a horizontal stretch or compression, you've got to factor out that coefficient of x. All right, so any questions on what happens when the center is not a nice pretty integer? So last class we added a piece of green paper to your file folder. If you want to take out that piece of green paper. And I had you write some special Maclaurin series on the back of that green sheet. It's also helpful on those common series to write what the radius and interval of convergence is going to be. You need a green sheet, don't you? Yeah, you'll have to copy it. Remember, Taylor-Maclaurin series are special examples of power series. I'm not going to rewrite out what all of these series are because we did that on the green sheet, but what is helpful to know and to add to that is what the interval of convergence are to each of these special series. So for your Maclaurin series e to the x, the interval of convergence is all real numbers. And like I said, we wrote all this out on your green sheet. The interval of convergence for sine of x is also all real numbers. Cosine of x also has an interval of convergence of all real numbers. One over 1 minus x, remember, which is your geometric series. This one does not have an interval of convergence of all real numbers. The interval of convergence is just going to be from -1 less than x less than 1. Again, you could always find them if you forgot. But again, because these are your common ones, it's also very helpful to know the interval of convergence of those. All right, so any questions on that? All right, as I mentioned before we went to lunch,